Good afternoon, good morning, good evening, everyone. On behalf of President Salvo Balio, President of the Instrumentation and Measurement Society, I welcome you. Welcome to the third and final lecture in the Spring 2021 Virtual Distinguished Lecture Webinar Series, sponsored by the IEEE Instrumentation and Measurement Society. My name is Judy Sharman. I am the Operations Manager for the IMS. I want to give you just a short introduction to our society. Our field of interest is the Instrumentation and Measurement Society's field of interest is the science, technology, and application of instrumentation and measurement. If you are not a member of the IMS, we warmly welcome you to join us. You can find more information on our website at IEEE-IMS.org. And now we're going to get right to the heart of the lecture with our speaker, Dr. Daniel Watznig. He is from the Institute of Automation and Control at Graz University of Technology in Austria. He is a full professor of autonomous driving. He also is the EIC of the SAE International Journal on Connected and Automated Vehicles. He's an invited lecturer at Stanford University. And last but not least, he's the founder of the Autonomous Racing Graz team in the Global RoboRace race series. Daniel, I'm pleased to turn this over to you. I will stop sharing my screen and turn it over to you.
So, Judy, many thanks for your kind introduction, and you're welcome to everyone who is already in the webinar. So give me a second, let me just share my slides for today's lecture. And go to presenter mode. All right, very good. So yeah, today we're gonna get a bit of, let's say, insight in the topic of multi-sensor perception and data fusion, which is a very important and active field in, let's say, in the topic of autonomous vehicles. The main idea of autonomous driving is that you have three building blocks: the sense block, the planning block, and the actuation block. And today we're going to focus a bit more on the perception layer, on the sense block, where we have a suite of sensors that are needed and required to perceive the environment. The idea or the course of today is I'll give you a general introduction to autonomous driving, since I believe that not everyone is directly involved in that field or actively researching that field. Afterwards, I would like to give you a short motivation about sensor fusion, why we need sensor fusion. Then I would like to introduce the different fusion taxonomies and continue with a couple of examples, starting with a very simple one to motivate the topic of sensor fusion. Then we will discuss a bit how fusion happens on detection level. And finally, I would like to show you the vehicle pose estimation, which is pretty important, because if you drive autonomously, you need always to know where you are. So you need the position in real time. And of course, there are problems, there are open challenges, and I would like to focus the end of my talk a bit on the current existing problems that need to be solved. If we talk about autonomous vehicles, we know that's a let's say a hype topic for a couple of years meanwhile, and the benefits are still there. So we expect a couple of benefits, and those are listed here. So we expect that the safety is improved, that we see less road fatalities, and that crashes are mitigating. So that's one of the important things if we can shift, let's say, to autonomous operations. Then we expect that the energy use is reduced and also the emissions, because although we see a lot of prototype vehicles which are gasoline or diesel vehicles, the future of autonomous vehicles is always electric. So we talk about purely electric, purely battery electric vehicles there. And if you talk about trucks and platooning, of course, we expect, and it's already proven, that we have some improvement in terms of aerodynamic situations. That means the aerodynamic drafting definitely improves. Then if you talk about, let's say, our big cities, about mega cities, we expect that the traffic throughput gets better, that we have less congestions, that we have, let's say, improved usage of the capacity of the roads within the cities. And that, of course, is a comfort topic. Then we actually would like to see this new so-called mobility as a service, MaaS, which means that we have concepts, shared mobility, but also multimodal mobility, that an autonomous vehicle in the city is just one part of the entire journey, because you start from home to your destination, and you might use a bus or a train or some other modes of transport, and it's just seamless integrated, and you just use your app and that's it. That's a pretty hype topic, MaaS. Of course, there is still a lot of research to do and a lot of discussions ongoing there. And last but not least, it's actually a great thing to get handicapped people and elderly people back to mobility. And in the end, when we talk about autonomy, it's let's say there are three pillars. It's comfort, it's efficiency, and it's safety, where we expect improvements. Where are the current challenges? Why there is still a situation that we cannot buy such a car? We read a lot, we see a lot. Waymo is driving around all the time. We see the cars driving around in California, Nevada, and Arizona. We see all around the world activities. But if you go to a car sales place, we cannot buy such a car. And you see there are a couple of issues. And I just had a kind of a color coding. The blue ones are the technical challenges. Then we have the legal framework and the ethics situation, which is still not in place everywhere. And the customer acceptance and the trust in the technology, which is pretty important. You have to trust, otherwise you will not spend a single dollar to buy such a car. If you look a bit deeper in the technical challenges, I just grouped it in let's say, in pretty randomly there. So the one issue is still on the sensor side. The sensors still are not there where we would like to have the sensors. There are still imperfections, degradations of sensors, bad weather conditions are not very helpful there. Then in the next step, if you talk about the perception, you need to model the environment. We will come to that later on. You need to detect and avoid false positives, false alerts. You need to be sure what you are detecting and avoid that you detect artifacts and do some wrong decisions there. And then, of course, the decision-making itself, decision-making under uncertainty is a pretty unsolved topic so far. Then how to deal with AI. It's pretty common that we need AI for the camera. So AI is already in place. Whenever you need a camera, you need artificial intelligence for the, let's say, semantic, for the segmentation, that you could work out what's in the taken picture in order to process the data. But if we talk about other parts in the car or in the truck or in the drone where we could use AI, there is a huge field where we can actually put in AI, but the main issue is how to prove the safety of artificial intelligence. Then if a driver is involved, there is one level, and we'll come shortly to that, where it's considered that the driver takes over, that we have takeover scenarios. How could that work? How can we ensure safety there? Then it's meanwhile agreed that we need the infrastructure. Just having the vehicle, the ego vehicle with a, let's say, very expensive set of sensors is nice, but still a prototypic situation. When it comes to a rollout, we need the connection to the infrastructure, and that could be the Wi-Fi standard, that could be 5G, maybe 6G later on. So this embedding of the car in the digital infrastructure is an ongoing topic. And of course, how to assess reliability, safety, and security, how to quantify. And that goes along with globally agreed test scenarios, test requirements. So we need to know to test against what. We cannot test against everything, against every rare event. That will not be possible. It's just not feasible, too expensive. But in the end, we need a certain set of scenarios, like in US NCAP or Euro NCAP, where you test your passive and active safety. There is a agreed standard, and given that, you get the stars ranking, you get a type approval on that. That's not yet there. And if we quickly look, and I don't spend a lot of time for that, it's, I think, pretty well known that we have the levels of SAE. They have been defined 2014, then updated 2018, and we have, let's see, the blue part, which is level 0, level 1, level 2. Level 2 cars are on the market. So when you buy, let's say, a car in 2021, it's a level 2 car. And when it becomes green, then we talk about automation. And level 3 is actually a scenario where there is a handover takeover expected, most likely for highways. So you drive manually to the highway. Once you're on the highway, the car takes over. And once it's time to exit, you get right in time informed by the car, please be aware, you have to take over, we are going to exit. That's the scenario for level 3. It's definitely not desired, or it's not in place that in urban scenarios, in critical situation, the car suddenly gives the signal, please take over, and you have to manage a very critical situation. That will never happen. It's just it's a comfort level. And level 4 is the next one. That's the first level where we actually do not have any blue part in there. So the machine takes over. That means the machine is in charge for the entire driving task, with the restriction that we have so-called a predefined ODD, which stands for Operational Design Domain. That could be just on the highway, that could be just during daylight. So whatever my entire set of scenarios constraints, that is immediately level 4. And level 5 actually means that's the robot taxi. The car is able to handle any situation around the world. If you're driving in the Rocky Mountains, the car is able to deal with that. If you drive in the Sahara in Africa, the car is able to deal with that. If you drive in Tokyo, the car is able to deal with that. What I'm saying is that level is a bit of artificial, so we might not see that within the next couple of decades, because it's just too complex to be able to deal with any situation that ever could occur. If we talk about sensor fusion, first, I think I would like to motivate with a short video. What we see right now is what the car receives when it just has a camera. So that's a Mobileye camera, that's a provider from Israel. We get information from other objects. Now we see the radar signal. So the radar reflections are coming in. So now we have camera and radar in place. And in a second, we will see the third sensor, which is pretty common. That's the LiDAR sensor, the laser scanner, that gives us something like a point cloud. In that case, we have 16 vertical layers. That means we get vertical information. And now we have, let's say, a set of signals that the cars actually get in. And now the situation is how to work with those signals to come up with a final decision, how to drive, how to calculate the trajectory. And the overall idea, basically, of sensor fusion is to reduce the detection uncertainty. And this example actually shows that if we consider a radar and the camera, they are pretty in contrast, but they are regarding their features. The radar has a very accurate depth information, while the azimuth direction, so if the radar sensor is mounted here, is not very sharp and not very highly resolved. And the camera is exactly behaving the different way. And what we actually get out is, if we combine the blue elliptical shape with the red one, we could actually reduce the uncertainty. And that means we are getting more accurate. So that's one of the motivations of doing sensor fusion. And this small video from the company Base Labs actually shows how that actually works. A car from behind is passing by the green box. We see, here is the green car. We see the estimate along with the covariance. And if we just use one sensor, now we are using 3 sensors, the fusion 3 sensors, we see that the covariance is very small. And if we have, let's say, that's the statement or the takeaway, if we can fuse the data from different sensors, we can reduce the variance. That's also the covariance. And as you can see here, the variance is immediately increasing if we just have one sensor in place and not 2 or 3 sensors. What you see right here is a fusion of camera and radar only. So radar in terms of long range radar, but also short range radar. So three sensors, but only 2 modalities are in place. And another way of doing sensor fusion is just looking beyond the car and using the infrastructure. That could be the wireless signals via the Wi-Fi standard or 5G signals, but also stationary radar sensors or stationary cameras. And the main idea is if we can use data, and if we use data from the infrastructure, we could extend our field of view by a certain factor. As factor 3 is one rough estimate there. So usually we have the radar and the LiDAR with 250 to 300 meters. So that's where we are. And we actually could come up almost to 3/4 of a mile, something like that. So another way of doing fusion. And if you just put all together, in our group, I'm pretty aware that we are all experts, and we have a couple of drawbacks if we use single sensor perception. And one of the critical things in driving is if we have artifacts, and that means the sensor is detecting something which is not there, and then there is an action that should be avoided. That's a very critical thing. And also the other way around, the false negatives, the sensor is not detecting, although there is something around and we hit, in the worst case, a pedestrian. That's also a critical thing. But in the end, we have to deal with false positives and we have to deal with false negatives, because we have probability density functions, and we unfortunately cannot avoid those false alarms. And if we actually can come up with a fused unit, we actually get a lot of benefits, and that could be, of course, the increased classification accuracy, state estimation is improved, the robustness, in availability. That means if one sensor breaks down or degrades, there might be another sensor that is able to take over. And just shown in the previous slide, we expect an enlarged field of view if we get signals from the infrastructure. On the downside, we need to deal with a higher price, of course, and we have more sophisticated algorithms, and not all of the platforms, of the computing platforms in cars are suited to run extended Kalman filters or more sophisticated filters that might be there. To show you very briefly the overall architecture, you see in the center of this sketch, there's our fusion unit. We get the inputs from the sensors. We have the fusion unit that is more or less in charge to create the environment model in real time. And then we actually influence the planning algorithm. The planning algorithm usually has 3 layers: the strategic layer, the tactical layer, and the reactive layer. And those 3 layers are, if you look time-wise, very different. The highest level is, we are talking about 10 seconds and even minutes. That's the destination. I'm driving from A to B. That's the navigation part, the route planning. The tactical level is the scenario itself. So I'm driving and I would like to merge or just bypass someone. That's let's say in the range of 1 second up to 10 seconds. And then we have, let's say, the most critical part, the reactive level, when a kid suddenly jumps in and we immediately have to react and to avoid an accident. And that is in the range of 10 milliseconds up to 100 milliseconds. And we have the active safety. That means avoiding any accident, and that goes across all layers. So the sensor fusion is pretty important to get the planning algorithm feed to get, let's say, a reasonable input for the planning layer. And just open this slide. In total, what we see here, it's just a different view of the overall architecture of an autonomous car. We have a suite of sensors. We have the fusion part and the data processing. We are going to talk about that one a bit more in detail. We have then the green part, which is the scene understanding, the decision-making, preparation of decision-making, and also the planning of the next few seconds of the trajectory, or in the best case, you propose a bunch of trajectories just to make sure if there is an unwanted and unpredicted event that you still can switch between trajectories. And the last part is the low-level control, longitudinal and lateral control. It means that's the actuation of our car. And the last block is the blue one, which is, again, a pretty important block, because that one takes care that everything in the car works properly. It means you have to make sure 24/7 that the software is doing right, that the sensors are doing right, that any hardware piece is doing right. And that goes along with this topic of fail operational behavior. And fail operational means if one component breaks down, there has to be a second component that takes over responsibility. In the avionics, we have triple redundancy, which actually means you have usually, just talk about control units or flight units, 3 different flight units with the same task. They are from different manufacturers, and the software is coded from 3 different software teams. So you try to get avoid of random errors, but also systematic errors. And of course, triple redundancy will not work in the automotive. It's just too expensive. Pretty short, if we talk about our sensors, we have cameras, we have radars and lidars, and all of them have certain pros and cons, benefits and disadvantages. Cameras are in place in the cars, they are very cheap, but they do not work in dark conditions, for instance. And if we have bad weather, same situation. For the radar, it's again a sensor that is already in cars. For instance, for ACC, the adaptive cruise control, it's pretty cheap and it performs well when it snows, when it rains. It works pretty good. It has a low resolution and it has some issues with static objects because we have, as we've seen before in this pretty small example, a very bad resolution in azimuth angle. And if we have metal objects to the left and to the right, we get interferences and also artifact detections, which is not that good. The LiDAR is pretty expensive. It's still expensive, but it's definitely immune against darkness and illumination effects. It has the best resolution. It's still, let's say, a bit oversized. You could put it on the roof of the car, which is not very good. But meanwhile, you could mount it like the radar sensors around the car. But we still have the issue that it's a sensor which is not, let's say, fully in industrial operation for automotive purposes. And it's still a discussion. Right now, we have time of flight LiDAR sensors. The first prototypes have been already proposed regarding frequency modulated continuous wave, which are always eye safe, and they use less power for the same distance. And due to the effect of less power, we can use smaller antennas and the overall size gets smaller, but they are in the prototypic phase. Coming back to our environment model, we get to the left, the input are the sensor signals, and we get, let's say, or we expect a lot of data coming out of our model. And that, of course, is the list of vehicles, the pedestrians, so all dynamic objects, all static objects, lane points, the yaw rate, velocity. And there are 2 ways that can be used to fill the environment model or to work out the environment model. The one approach is the object tracking approach, where we have a sensor that is able to track the object. Usually the Kalman filter is used for that, the extended Kalman filter. And we have a moving object, T0 up to T3, and you just track this object with the Kalman filter. It's getting more critical if we have more objects, more than one, because then we actually need to work out what data, what observations belong to which object, to which track. That's called data association, an active research field. But multi-object tracking is a pretty common approach. And the other approach is also a pretty common one. That's the occupancy grid filtering. You just discretize the field of view in front of you in small cells, in rectangular cells, and you define 3 states: free, occupied cells, and unknown cells. And if, for instance, the laser beam gets a reflection somewhere, we immediately know in between we have free cells, we have then an occupied cell, and behind the occupied cell we just don't know, so it's unknown. And by using evidence theory, Dempster-Shafer or Bayesian, the Bayesian framework, we could actually work out the fuse up, let's say, using occupancy grid filtering for fusing the data from LiDAR along with radar and also camera. If you talk about the fusion taxonomies, we end up in 4 different definitions: fusion classes, architecture, taxonomy, data related, and the fusion level. So through, in fact, we have 4 ways to explain sensor fusion. If we quickly go through those 4, starting with the first one, fusion level. Fusion level actually is are also named as low-level fusion, intermediate-level fusion, and high-level fusion, where on the low-level side, we deal with the raw data, with the signals, so we do not throw away any information. And then we actually already filter. We just work out features from the signal, then we are in the intermediate phase. And if we have already decisions, that's a car, that's a pedestrian, and we fuse the data on that level, we talk about the high-level fusion. It's the first way of talking about fusion. Second way is we are talking about classes. Competitive, complementary, and cooperative fusion are the three ways of doing different fusion classes. And competitive means we have just two radar sensors, so the two sensors, same sensor modality, and they're just competing. Complementary is that we, of course, find a sensor that is more or less complementary to the radar. That could be a LiDAR if you talk about range estimation. And cooperative means that we, for instance, include GPS with stereo odometry, vision-based odometry to work out our position, for instance. Third way is more hardware related. We actually talk about centralized architectures, decentralized or distributed architectures. If you look here, for the centralized, we see we have our sensors S1, S2 up to Sn, the sensor pre-processing. Then in our fusion center, we have let's say the alignment, temporal and spatial alignment. Then the data association and the estimation. That could be the occupancy grid, could also be multi-object tracking. So that's the centralized version. Decentralized means that we actually have, let's say, for each sensor, this operations, the signal processing pipeline. And for the distributed architecture, it actually means that the different processing pipelines are also distributed to different cores of a GPU or to different control units. And finally, we have to talk about, let's say, when we are measurement engineers, for the data-oriented topic, which means how to deal with uncertainties. And we all know that the sensor, when we measure something, we always have an uncertainty. It's always statistics. And we have to deal with uncertainty, with vagueness, with ambiguities in the data, with incompleteness, correlations, and all of those kind of things that have to be considered somehow. And we all know that, unfortunately, it's not only uncertainty without vagueness, it's always a combination. And we have to deal with that. And there is a nice paper from 2016 where your nice overview has been presented, what kind of influences are in there. Imperfection, disparateness, inconsistency, and correlation are the main sources that are data related. And of course, imperfection means we have uncertainties in the data, we have imprecision due to the sensors, we have, as I said before, ambiguities, incompleteness of data, or sparse data, whatever, that have to be basically worked out. And if we talk about the algorithms, and I will not spend too much time talking about the algorithms, you could imagine there are so many algorithms around. Statistic-based, deterministic-based, but also knowledge-based ones using fuzzy logic, so rule-based operations, but also neural networks are in place. So there are so many algorithms out there, and if you really focus on sensor fusion, you will see it's a bit of work to get to dive into all the algorithms that are already out there. If we talk about a few examples, let's start with a very simple one, and this very simple one is we have two sensors. They measure the distance to one object, and we just assume we have two radar sensors. They actually have the same. They provide the same measurement. So we talk about competitive fusion, and we assume that the data is normally distributed around. So we have a mu1, a mean mu1, and the standard deviation sigma 1, the same for sensor 2, and we just assume, for our example, that the sensor 1 is better than the sensor 2. Sigma 1, or also the variant sigma 1 squared, is smaller than sigma 2 or sigma 2 squared. If we deal with Gaussian variables, or Gaussian random variables, the fusion is pretty easy. We just have to multiply, and we come up with the fused data. So that means that D, our result, is again, of course, Gaussian distributed. And D is actually the multiplication of D1 times D2. And what's the result? And I think that's the important thing. Without deriving the equations, we can work out mean and variance, just working and calculating with expectation values. But we get, let's say, a nice result. And this result reminds us pretty pretty clearly to dealing with or calculating parallel circuits. So working out the overall resistance of a parallel circuit. And what we get out of this main idea is that the overall variance is the smallest in our system. It means even if our sensor 1 is better than sensor 2, so the blue curve is just more distinct and is more peaky than the red one, the overall result, the yellow one, is even smaller. So we have a better variance for our result. And that's the great thing, that the overall uncertainty always decreases if we fuse the data. From the data-related point of view, a great achievement. Second example, very short example, is how we have seen the video of Base Labs where radar and camera data have been fused with the extended Kalman filter. And if you use the Kalman filter or have already used, you know, we need a state space representation. We have our evolution of the states, and we have our measurement equation. And the Kalman filter actually works out the belief in our state, in our unknown state. So we are interested in estimating the state. That could be, if we talk about Bose estimation, that could be in this vector, that could be the position, velocity, and acceleration of the autonomous car, for instance. And the measurement data, they go in our, let's say, measurement matrix, capital C, along with the measurement uncertainties. And here, actually, the fusion happens. And then we actually have just to run the Kalman filter, go for the prediction and the correction. And without going into details about the Kalman filter, that's a standard approach in sensor fusion. If you fuse radar data with camera data, or as I said before, for position, if you fuse GPS signals with the IMU, the inertial measurement unit, and maybe LiDAR for localization, you basically go exactly that way, that you just apply the extended Kalman filter. And just very short, without going into detail, the Kalman filter or the extended version has some issues because we need to know pretty accurately our process noise and our measurement noise. That means our covariances QK and RK. So our noise processes have to be defined, and we always get, let's say, the smallest possible standard deviation. It's the best linear unbiased estimator. So we get always by the principle of the Kalman filter, the smallest possible standard deviation. But sometimes, and especially when it comes to industrialization, we are interested in just having a look at the worst case to see if even for the worst case, we are still safe. And one filter or one approach that works for that is actually the H-infinity filter. And the H-infinity filter is, let's say, an advancement of the Kalman filter. It's also called the min-max filter. And the great thing that comes on top of the benefits of the Kalman filter is that we are, on top of that, we can deal with dynamic uncertainties. That means uncertainties that change over frequency, and also with parametric uncertainties. That means we can deal with parameter tolerances, parameter degradation, so that the system is changing. And not only the measurements and the measurement uncertainties, so it's a bit more general approach compared to the Kalman filter. It's just a kind of an outlook what algorithms could actually work, and which are already discussed and also implemented and published. Let's go to the vehicle localization example. That one actually, I would like to show you two different examples. The one is using just a LiDAR for localization, and the other one, and that relates to, let's say, autonomous racing. Julie was mentioning that I founded a team some years ago that's continuously competing in the RoboRace series. Here we have the situation that we have edge cases, high dynamics, high speeds, but we have autonomous cars, all the sensors. So the same, so the hardware, talking about the sensors and the computing units are pretty much the same like we have in cars, but of course the scenarios are different. And I will just to show you there what kind of problems arise when we have those kind of applications. The first thing, and I just decided to put that one in, is there's been a nice white paper published by the industry in 2019, end of 2019. Daimler or Mercedes was in lead for that paper, and a lot of car manufacturers, but also suppliers like like Denso or like Continental or Bosch did contribute there. And what you see here is that they defined 12 capabilities, starting, let's say, let's say capabilities that have to be considered for certain functions. And the functions are written there, and they are distinguished between FS, so function S, and function D starting here. And the difference of what is S and D standing for: S stands for safety related, while D stands for degradation related. So there might be degradation, and what kind of capabilities have to be considered if we have situations where we have to deal with degradation. So that's the idea. That's the matrix, and we just see a couple of crosses, and we also see that security and safety assessment is pretty important because it just affects every little thing in an autonomous car. Coming back to our topic fusion, first thing, and that's FS1, is actually localization. It's safety critical, and for localization we already need, so when we talk about, let's say, safety critical or safety integrity levels, we come across ASIL A up to ASIL D. ASIL D is the most critical one. Starting from ASIL C, we need redundancy, and that means for localization, we already need different sensors. Usually it's GPS and IMU, could be extended by LiDAR sensors. But already here, we need the sensor fusion in such a car. And for the next step, perceiving the environment, same situation. We again have radars, we have LiDARs, we have cameras. We need the localization because we need to know where we are. So localization already has some sensor fusion done. So we have, let's say, a sequence of sensor fusion, but even for this very complex block here, we see that's the critical thing, because in the end, we need our environment model in real time. And that has to be, we have to believe in that one. And that makes the things a bit more complicated. And that's maybe also why we don't see autonomous cars in just around the corner, and we cannot purchase those cars. I just brought two examples. The one is a passenger example. The other one will be the racing example. That's just a very, very common sensor setup. You see that kind of cars everywhere in the world. It's an American car. It's a Ford Fusion. And this Ford Fusion is equipped with, in that case, with three LiDAR sensors on the roof. There is a long-range radar right here. We have a short-range radar that they are hidden behind the bumper. There are 4 in every corner. Then there are, let's say, a set of cameras. Right here is a camera. And here is the A pillar. There are usually cameras, also C pillar, and of course backward looking. Yeah, there's a lot of stuff in the booth, of course, for doing the computation. Usually you have, and that's I would say there are different ways to come up with such a car, and there are different software stacks around. The most common software stacks are the AutoWare software stack, which is an American solution. The Apollo software stack, which is driven by Baidu, it's an Asian solution. We have in between also the DriveWorks of NVIDIA, again, an American solution, and some, let's say, solutions which are not that mature. AutoWare is pretty advanced. The company Apex AI in Silicon Valley has just published last week that they managed that their operating system is now functional safe. That means it can be qualified, and it can be certified, and it can be used in cars. A very important step in the world of autonomous cars. But coming back to the implementation, what we see here right now, and I just provide you with a few videos, that's what the car sees when it gets the radar signals. And we can distinguish between the cluster mode, the raw data, or the object mode, where we fuse already an object level. As we have discussed right before, we could go for low-level fusion or high-level fusion. If you look at the LiDAR situation, then what we see here is, so the video to the left relates to 1. So all the ones we are seeing here in the list are shown in the left video, while the 2s are shown in the right video. You've seen before the car has 3 different LiDAR sensors. And that means first we need to calibrate the LiDAR, then we need to load the map. If you do LiDAR localization, you need, of course, to drive around the track upfront. You need to store a LiDAR map. The same thing if you you also need an HD map for the, let's say, for the region where you're driving around. That's for the LiDAR pretty much the same. You need a pre-recorded LiDAR point cloud that is stored in the car. So that's the next step. You just load the data, then you do the LiDAR localization with the 3 LiDAR sensors. You have to normalize it, and then it starts with the 3-dimensional filtering. You do the point cloud transformation because the 3 point clouds are in different coordinates, and then you fuse the point cloud. And in the next step, of course, you need to do the ray ground filtering, the clustering of the points, because as you can see here, we have so many points in our point cloud from the LiDAR reflections. We need to find the cluster. Otherwise, we will not be able to compute that in our platform in the car. And finally, we are interested in bounding boxes. That means we would like to see cars, pedestrians, so the object levels, and that's what we see here. So again, we see first the point cloud transformation, the fusion happening now. In a second, we'll see the ray ground filtering. All right, here we are, and then we start with the clustering. That means we just, with some smart algorithms, we are working out what right now the clustering happened, which points belong to each other, and then finally we fit boxes to the dynamic objects. That's the standard way that everyone around the world is currently using, if you use LiDAR for localization. And to make the picture complete, or to complete the picture, you usually have the steps loading the map, then you have to do the localization. Once you know where you are, you are now able to drive, then you need the object detection and of course the path planning. So that's the path planning layer. And it looks like this. First you define the global planning. I would like to drive from a current position to the destination. That's the global planning. And the local planning is what I mentioned before. The car is based on the sensor fusion unit, calculates a bunch of trajectories, and those trajectories are then calculated and they could be driven, and then you just check if they are feasible or if they are infeasible. And if they are red in this example, then you can't drive those. If they are green, then they are let's say a very safe trajectory, and the other colors are just you can drive, but you should always look for a green one. And if you look here, the red ones are the situation here. There are 2 pedestrians, and you have to keep a certain distance to the pedestrians. Yeah, and the camera-based part looks like that you just use algorithms like YOLO. You only look once. That's an open algorithm that can be used by everyone in the world, and that comes already with, let's say, classification of truck and persons or cars, and this information is then used to fuse with the LiDAR object and the radar object. Then we are talking about high-level fusion on object level. All right, then I promised to give you a very quick insight in let's say, in the RoboRace competition. That's the car of RoboRace. That's one of the cars. They are currently based in Las Vegas. The headquarters is in Los Angeles, and there are, let's say, races every 4th to 5th week. They are all in Las Vegas. The teams are sitting at home. So there's, for instance, MIT is one team, Carnegie Mellon University is one team, we are one team, University of Pisa in Italy is one team. So they are distributed around the world, and currently we are all competing remotely. Code is sent over to Las Vegas, then the engineers put it in the car, and then the car is driving, and who is doing best in the end is going to win. And the overall, let's say, the overall challenge, of course, is it's from the RoboRace point of view, how to attract a fan base. That's their business. From a technical point of view, there are a couple of, let's say, very interesting challenges, and that's how to achieve the same performance like a highly skilled race driver like Lucas di Grassi is able to achieve. So that's one of the, it's a classical optimization problem. The other thing is precision, how to localize within 10 centimeters at high speeds, and that's the thing that makes it a bit more challenging. And finally, the current competition is there's only one car at once on the track, and that will change by the end of this year when the developments and advances are there. And that's a safety issue, that we can send out more than one car, and we are able to bypass and to really have a race where the teams are competing. And coming back to the sensor fusion topic, one critical issue there is basically that we have different sensors with different sampling times. And it means you need to come up with a proper vehicle motion model that explicitly mentions the sampling time. Otherwise, you cannot get rid of this issue that the different sampling times are coming together. And the worst case is, and I show you in my last slides, what could happen if you do not consider the sampling times properly. So that's just the architecture of the RoboRace car, and you see they are equipped with all the relevant sensors. The teams can decide which sensors to use, so there is no need to use all. It's depending on your implementation, of course. And the typical fusion problems actually are, I think they are pretty obvious. We have sensors mounted in different places. It means we have to align time-wise and space-wise. We need the temporal and spatial synchronization. That sometimes is forgotten because many people just take the data and run a Kalman filter and that's it. Then you have to deal with bias due to transforms, also due to the measurements, correlation in data, also the data association problem that I mentioned before when we have different targets that have to be tracked. And finally, we have this issue of out-of-sequence measurements. And that means, and that's very short now, if we have two sensors, so we have two Kalman filters, and then we have our fusion center. And if we have this example that sensor 1 takes pretty long for data acquisition, processing, transfer to the fusion center, sensor 2 starts later, but finishes earlier, we have to really take care that we fuse the right data, because right here in the fusion center, we just get data from sensor 1. And the worst case could be here that we get previous data, which is already history from sensor 2 and updated data from sensor 1. And the worst case that happens is actually, and that's this small graph, for this example, we drive with 130 kilometers per hour. And in the worst case, if the time step error is pretty high, look at that, for instance, 30 milliseconds, we end up that we estimate our object in front of us 1 meter to the left or 1 meter to the right. And that's a critical thing, because then your decisions might be the wrong ones. Even if we have, let's say, in a city where we allow to drive slowly, it could happen that we estimate, or we just do the wrong decision. We just decide, okay, they're the pedestrian, we can easily evade, but in fact we did let's say a wrong estimation and we hit the pedestrian, and that's pretty critical. So that means before running any filter, take care on the measurement data, and that brings me to the final slide, to the conclusion for today. We definitely, without fusion, autonomous driving will not work. So that's set. And we actually have to think about that we decide on algorithms and choose those algorithms that are designed with the right speed and accuracy requirements. So racing is completely different to people movers and completely different to trucks and completely different to passenger cars. And we have to make sure that we have to consider all the possible error sources that might happen. And also if things like GPS are providing failures, or even if we have things like spoofing or jamming or beaconing, then we cannot trust the localization with GPS, for instance, or GNSS in general, and that might make things pretty complicated. Having said that, I finally would like to thank you for your attention, and I'm looking forward to your questions.
Daniel, thank you. Thank you so much for this informative webinar. It was interesting, but honestly, it was kind of fun. We do have a couple of questions. You can find them in the Q&A. And Daniel, if you would read them out loud and then answer them. And if anyone has other questions, please put them in the Q&A and we'll get to them.
Yeah. So the first question actually is, if two sensors have the same field of view and sensor A is better than sensor B, so like the example, how could sensor B improve general performance? So the general performance, so if you talk about capability, then even if sensor B is doing, let's say, a very bad job, overall, the sensor B is still contributing to the overall performance, given that sensor A is better. When it comes to, let's say, breakdown of sensor A, then usually sensor B is still in charge, so that you can operate even in a degraded situation and come to a safe stop. So that's why sensor B is still pretty important, although sensor B is maybe just referring to my example, definitely not the best one for the range. We have the range estimation example, but the overall performance, you have to view it in that way that sensor fusion is not about only accuracy. It's actually about ability, about robustness, and fail operational behavior. I hope that helps somehow. Then I would just read the next question. Could multiple LiDARs practically increase the limited LiDAR resolution performance? For example, 2 LiDARs with almost same field of view increase resolution from 0.2 degree to 0.1 degree. Yes, that's right. Just looking at the let's say, just reading once again, same field of view, but I guess the LiDARs are different, because in order to increase the resolution, if you fuse the 2 LiDAR signals, the 2 LiDAR point clouds, you definitely can get or increase the accuracy in the resolution, given that you just apply the formulas we discussed before. And it has been investigated basically to apply more than one LiDAR for the same situation. It's usually used for drones, for instance. In the automotive world, it doesn't make a lot of sense, because usually a LiDAR has, talking about Velodyne or Ouster, they have a resolution of 0.1, which is let's say pretty good, and it's actually not really needed to have such a good resolution in the classical passenger car segment. It's just too it's too accurate. It's a bit academic. For industrial usage, you actually don't need that kind of accuracy. The same thing for localization. Even if you could localize meanwhile using LiDARs for, let's say, 2 centimeters up to 5 centimeters, the industry just needs some 25 to 30 centimeters localization accuracy, and that's why, of course, but that's our job in the academic world, to come up with solutions which are even better for the industry. Sometimes they need let's say practical solutions, and might not need that kind of, let's say, resolution and accuracy that we actually researched. Then we have next question: how are measurements associated to objects? Yeah, so that one is referred to this topic of data association, and usually, so the standard algorithm that is in use is the so-called global nearest neighbor, GNN, using the Hungarian algorithm. So you just work on the Euclidean distance, and you work out which data belongs, or you're fitting in the least square sense a track, and then you're working out which data is closest according to Euclidean distance. So that's a common approach, and you could easily find examples that show that this approach is not working. And quite recently, other approaches have been proposed and published. They are more in this statistical motivated, like the joint probability data association approach, JPDA, for instance. But in fact, you use GNN and Hungarian. So if you just search for those keywords, you will find, let's say, the most common results for doing the data association from observations to objects. And you also can, just as another comment, you could also, well, in many cases, the Kalman filter is used, because data association always goes along with Kalman filtering and multi-object tracking. The Kalman filter is usually extended by a certain additional feature, which is called gating. So you define certain gates, and you just analyze the observations which are in this gate. Then you're applying the GNN, and then you decide which data is used for correcting your next step in the Kalman filter. So I hope that helps.
Thank you, thank you. I don't see any more questions in the Q&A. I want to again thank everyone for your participation. This is being live streamed on Facebook, so you can go to the Instrumentation and Measurement Society page on Facebook and view this recording. And it will also be available on the I&M website next week. So tell your colleagues if they've missed it, they can catch the recording. Thank you again. Thank you, Daniel, and everyone have a wonderful day. Yes. All right. Bye-bye, everyone.
Same to you.
Bye-bye.
Have a great day. Bye-bye. Thanks to all.
Bye-bye.
Bye-bye.